Welcome to this lesson on integration of logarithmic functions. Today, we'll learn how to find the antiderivatives of functions involving logarithms. Integration is a fundamental concept in calculus, and logarithmic functions appear frequently in many applications. Before we start with integration, let's quickly review some important logarithm properties that will help us understand the integration process. Remember that the logarithm of a product equals the sum of logarithms. The logarithm of a quotient equals the difference of logarithms, and the logarithm of a power equals the power times the logarithm. Also recall that the natural logarithm, ln of x, is the logarithm with base e, where e is approximately 2.71828. To understand logarithmic integration, let's first recall the derivative of the natural logarithm. The derivative of natural logarithm of x with respect to x is 1 over x. This tells us that the natural logarithm is the antiderivative of 1 over x. In other words, the integral of 1 over x is the natural logarithm of the absolute value of x plus a constant. Let's start with a simple example. Example 1. Find the integral of 1 over x dx. From what we just learned, we know that the integral of 1 over x dx is natural logarithm of the absolute value of x plus c. Note that we must include the absolute value signs because the natural logarithm is only defined for positive numbers, but the integral may include negative values of x. Now, let's look at another example. Example 2. Find the integral of 5 over x dx. We can pull the constant 5 outside of the integral and then use the formula we've just learned. So the integral of 5 over x dx equals 5 times the integral of 1 over x dx, which equals 5 times natural logarithm of the absolute value of x plus c. Now, let's look at a more complex example involving substitution. Example 3. Find the integral of 1 over x times ln of x dx. This is a bit trickier. Let's use substitution by setting u equals natural logarithm of x. Then do equals 1 over x dx, which means dx equals x do. Substituting into our integral, we get the integral of natural logarithm of x times 1 over x dx, which is the integral of u do. And the integral of u do is u squared over 2 plus c. Substituting back, we get natural logarithm of x squared over 2 plus c. Let's look at another example that requires a different approach. Example 4. Find the integral of natural logarithm of x dx. For this integral, we'll use integration by parts. Remember the formula. The integral of u dv equals u times v minus the integral of v do. Let's set u equals natural logarithm of x and dv equals dx. Then do equals 1 over x dx and v equals x. Applying the formula, we get natural logarithm of x times x minus the integral of x times 1 over x dx. This simplifies to x times natural logarithm of x minus the integral of 1 dx, which is x times natural logarithm of x minus x plus c. Let's visualize this result to gain intuition. Let's finish with a definite integral example. Example 5. Evaluate the definite integral of 1 over x dx from x equals 1 to x equals e. We know that the indefinite integral of 1 over x dx is natural logarithm of absolute value of x plus c. For the definite integral, we evaluate this at the upper and lower bounds and take the difference. So our answer is natural logarithm of e minus natural logarithm of 1. Natural logarithm of e is just 1, and natural logarithm of 1 is 0. Therefore, the value of this definite integral is 1. Let's visualize this as the area under the curve 1 over x from x equals 1 to x equals e. Now, let's summarize what we've learned about integrating logarithmic functions. First, the integral of 1 over x dx equals natural logarithm of absolute value of x plus c. For integrations involving logarithms in more complex ways, we can use techniques like substitution method, as we did when integrating natural logarithm of x over x, integration by parts, as we used to find the integral of natural logarithm of x. Remember that logarithmic functions appear in many real-world applications, such as population growth and decay models, compound interest calculations, information theory, and entropy sound intensity decibel scale. Thank you for watching. Practice these techniques to build your integration skills.